Hi, welcome to this presentation. We will be discussing how the recent addition of physics-based solving in the Jet Propulsion library enhances its steady-state capabilities to better fit industrial workflows. My name is Clément Coïc, and I will be presenting in the name of my co-authors Moritz and Mathis, as well as in the name of all the colleagues that provided their guidance throughout the development of this work. In this presentation, we will first introduce the industrial design workflows we refer to. These design workflows are relevant for the gas turbine industry, but not only, as they are generic to all model-based design processes. As this work focuses on steady-state simulation, but most of Modelica-related work deal with dynamic simulation, we will remind here the main differentiator between both. We can then discuss the enhanced steady-state capabilities added to the Modelon Jet Propulsion library. These will be illustrated by component and system examples. Finally, we will summarize these achievements in a conclusion slide. We will now introduce the industrial design workflows. Let's start with a basic example to illustrate the engineering workflows discussed in this presentation. Considering Ohm's law in its more simple form to characterize an electric resistor, we write that the voltage drop at the resistor pins is equal to the product of the resistor resistance by the current that flows through it. Typical simulation consists in providing the parameter R as well as one of the two variables, let's say the voltage V. The outcome of the simulation would then be the other variable, in our case, the current I. This type of simulation is also referred as off-design simulation. In opposition, on-design simulation expects both voltage and the currents at the design point to be known, and the outcome of the simulation is the value R. On-design simulations size the system. A newcomer in the Modelica world might wonder if there is a need for rewriting the equation based on the output we want to compute. A kind Modelica reference might answer that there is no need for doing so and that the compiler will take care about that based on the problem it shall solve. Eventually, these two persons get well along and decide to continue the discussion around a coffee table. The two simulation modes answer different questions. On-design answers the question, what should be my system design, while off-design answers, how does my design system behaves? It is actually meaningful to have this sequentially, defining the system design first and then evaluating its performances in a single model. Our Modelica compiler is able to prepare the model for both cases and hide the relevant equations and variables when not needed. In addition, with physics-based solving, we are able to add the modeler knowledge of physics and numerics in the libraries so that the model is more robust and efficient. This discussion illustrates a typical engineering workflow, and the stars on this slide highlight the key points of it. Later in this presentation, we will show how this is achieved within Modelon Impact using the Jet Propulsion library. Let's now move forward and discuss the main differentiators between dynamic and steady-state simulation. When performing a dynamic simulation, the entire trajectory of the variables is computed during the simulated time. If we are interested in the equilibrium of a system, we might thus need to simulate a long transient period before reaching the point of interest. On the contrary, with steady-state simulation, we specify the operating conditions of our system and solve directly the model at this point, ensuring that all variables are steady. Therefore, there is no notion of time with steady-state simulation. We directly obtain the result of interest. This brings lots of values, such as a simulation that is several order of magnitudes faster than dynamic simulation. It is easier to process the results, as only the point of interest is computed, and this facilitates the creation of sequential simulations to fit engineering workflows. It is now time to present how Modelon's Modelica compiler, combined with the addition of physics-based solving in Modelon Jet Propulsion library, enables robust steady-state simulations. First, we will introduce the dedicated capabilities of the Optimica Compiler Toolkit. Modelon's compiler is able to rearrange the acausal equations of a Modelica model into causal algorithm suitable for numerical simulations. It is also able to automatically derive the sensitivities relevant for solving optimization problems. While these features are generic to most Modelica compilers, Modelon Optimica Compiler Toolkit has the additional capability to hide residual equations and iteration variables from the solvers in a compiled model. This feature is key to enable switching simulation modes without recompiling the model. On the solver side, residual equations and iteration variables are scaled. The former is scaled based on the Jacobian, while the latter is scaled based on nominal values. The convergence is achieved when the exit criterion is satisfied. This criterion is based on combination of residual and step norm. Finally, in terms of debugging, the log messages are written in XML format. This enables automated post-processing. Optimica Compiler Toolkit provides dedicated Python packages for relevant tasks such as log or data parsing, as well as enabling user interaction with the equation system. On the library side, we take advantage of the compiler unique capabilities to add vendor-specific language constructs. These specify which equation should be considered as residual by the compiler and associated to which iteration variables. Holding of residual and iteration variables is possible through parameter conditions. Adding this vendor-specific language construct is referred as physics-based solving. The physics-based solving implemented in our libraries relies on Modelon insights about the physical properties of components and systems to achieve a structure of the system of equations that yields vastly superior numerical properties as compared to traditional automatic tiering algorithms. The physics-based solving is stored in an object-oriented fashion such that modelers can assemble systems graphically and the desired solving can be deduced from the model topology. For the Jet Propulsion library, we use generally accepted choices for iteration variables and residual equations from gas turbine community. Now we have all relevant notions in mind, we will discuss two separate component examples. The first model illustrates how we can change the type of parameterization after compilation. The second model focuses on and off design simulation modes. To highlight the flexibility of our product, the first example is run in a Jupyter notebook, interfacing with our compiler thanks to Python scripting, while the second example uses our cloud-based simulation environment, Modelon Impact. This experiment corresponds to a unitary test of the burner. An air mass flow rate enters the burner, is mixed with fuel, and then burned. The outlet combined flow is then evacuated through a duct to a pressure sink. In this Jupyter notebook, we first specify the model name and the required Modelica libraries, as well as all required Python modules. We then move to the simulation of the on-design problem. For that, we compile the model. We now load it. We will iteratively switch between the different parameterization options. These are specifying the incoming fuel mass flow rate, specifying the fuel-to-air ratio, or specifying the burner outlet temperature. The simulation is really fast, less than 0.2 seconds for all scenarios. We did not require recompilation, and luckily, all simulation gave the same result. The second example is presented in the Modelon Impact graphical user interface. Here, we can take benefits of the user-friendliness of this environment. For example, the library includes some predefined views for convenience. In this example, we will illustrate how on and off design simulations differ. In on design, the source pressure and mass flow rate are known, as well as the compressor pressure ratio. The outcome of the simulation are the map scaling factors of the compressor. For off-design simulation, these scaling factors are now fixed and both pressures at the source and the sink are known. The outcome is then the mass flow of air flowing through the system. Note that switching between on and off design did not require recompilation and automatically reuse results from on-design simulation as input for the off-design simulation. Let's now illustrate the speed and robustness of the steady-state simulation within Modelon Impact with a system-level example, a geared turbofan. A geared turbofan usually includes two main regions, the core region and the bypass. The split of the airflow between both regions is made at the fan level. The core region includes two compressor stages, the combustion chamber and the high and low pressure turbines, as well as the nozzle. The other nozzle evacuates the bypass flow. A gearbox between the turbine and the fan allows different rotational speed for efficiency optimization. Let's focus on performance and robustness. The model is compiled. We will now simulate the on-design mode. Switch to the off-design mode by unclicking the on-design parameter, simulate again, but without recompiling, however, reusing the sizing from the on-design mode. In both modes, simulation was fast and convergence was reached. To keep the demonstration simple and quick, we had already parameterized the model based on the following table. The design point was the top of climb. It is the most constraining mission point for the sizing of the gas turbine, optimizing the thrust-specific fuel consumption, while keeping the uniform blade temperature below 1240 degrees Celsius. Aiming at an entry in service in year 2035, the overall pressure ratio was set to 55. A small design exploration of the thrust-specific fuel consumption with regard to the overall pressure ratio is performed. From this plot only, we would be tempted to move to higher OPR values to leverage the fuel consumption improvement. However, due to material and cooling constraints, the uniform turbine blade's temperature shall not exceed 1240 degrees Celsius in all operating points. We witness here that an increase of the overall pressure ratio values based on a single design point would violate this temperature constraint during takeoff. This means that the next step is to actually simultaneously size the system at design point while verifying that all constraints are satisfied at off-design point. This so-called multi-point design methodology was led as perspective in the paper, but was performed since then. We invite you to watch the following dedicated presentation if interested. This concludes our presentation. We have introduced the on and off design terminology, as well as reminded what steady-state simulations are. With this in mind, we have described the industrial design workflow. We pointed out how our work enabled a robust and efficient implementation of this workflow. This was illustrated with component and system-level examples. Finally, we discussed the need for multi-point design and showed our graphical implementation of it. I would like to thank you for your time and remain available for any question.